Hi, this is David Quatello at Siemens. In this video, we'll be discussing the Siemens Quick Step Basics of Circuit Breakers. This course covers basic circuit breaker concepts and provides an overview of Siemens molded case circuit breakers and WL insulated case and low voltage power circuit breakers. You should have a basic understanding of electrical concepts to fully benefit from the course. And here's a slide showing the legal trademarks. Upon completion of this course, you should be able to explain the need for circuit protection, identify various types of overcurrent protective devices, explain the basic electromechanical operation of a circuit breaker, identify various types of Siemens circuit breakers, identify circuit protection ratings for various types of Siemens circuit breakers, describe time current characteristics on a time current curve, explain the benefits and function of the circuit breaker coordination, and identify internal and external circuit breaker accessories. This course has 4 parts plus a final exam. At the end of each section, there will also be a number of knowledge check questions. The first part is an introduction that covers basic circuit protection concepts. The second part covers circuit breaker concepts. Third part covers various Siemens molded case circuit breakers. And the fourth part covers Siemens VL molded case circuit breakers and WL insulated case and low voltage power circuit breakers. Let's get started. Current flow in a conductor always generates heat. The greater the current flow, the hotter the conductor. Excess heat is damaging to electrical components and conductor insulation. For that reason, conductors have a rated continuous current carrying capacity or ampacity. Overcurrent protection devices, such as circuit breakers, are used to protect conductors from excessive current flow. These protective devices are designed to keep the flow of current in a circuit at a safe level to prevent the circuit conductors from overheating. Excessive current is referred to as overcurrent. An overcurrent may result from an overload, short circuit, or ground fault. Some circuit breakers provide only short circuit protection, but many circuit breakers provide protection against short circuits and overloads, and some circuit breakers provide protection against all 3 types of overcurrent. Overloads and short circuits are discussed in the following pages. Ground faults are discussed later in this course. An overload occurs when too many devices are operated on a single circuit or when electrical equipment is made to work beyond its rated capabilities. When an overload occurs, damage to connected equipment or the conductors that supply that equipment can occur unless the circuit is shut down by an overcurrent protection device. For motors, like the one shown in the accompanying illustration, overload protection is usually provided by an overload relay. But for other types of circuits, overload protection is often provided by a circuit breaker. Every circuit requires some form of protection against overcurrent. Heat is one of the major causes of insulation failure of any electrical component. High levels of heat can cause the insulation to break down, melt, flake off, exposing conductors. A short circuit is a low resistance path for current created when bare conductors touch. When a short circuit occurs with voltage applied, the decrease in resistance results in a short circuit current that can be thousands of times higher than normal operating current. Ohm's law demonstrates the relationship of current, voltage, and resistance. For example, a 240 volt circuit with 24 ohms of resistance would normally draw 10 amperes or amps of current. When a short circuit develops, resistance drops. If resistance drops to 24 milliohms, current will be 10,000 amps. The heat generated by this current will cause extensive damage to connected equipment and conductors. This dangerous current must be interrupted immediately when a short circuit occurs. An overcurrent protection device must be able to recognize the difference between overloads and short circuits and respond in the proper way. Slight overloads can be allowed to continue for a short time, but as the current magnitude increases, the protection device must open faster. Short circuits must be interrupted instantaneously. Overcurrent protection can either be accomplished with a fuse or circuit breaker. Circuit breakers will be discussed in detail throughout this course, but first, it's useful to discuss how a fuse operates. A fuse is a one-shot device. The heat produced by overcurrent causes the current carrying element to melt open, disconnecting the load from the source voltage. Fuses without time delay provide excellent short circuit protection. When an overcurrent situation occurs, heat builds up rapidly in the fuse. Fuses without time delay usually hold 500% of their rating for approximately 1/4 second, after which the current carrying element melts. This means that these fuses cannot be used in motor circuits, which often have inrush currents of greater than 500% while the motor is starting. Time delay fuses provide overload and short circuit protection. Time delay fuses usually allow 5 times the rated current for up to 10 seconds to allow motors to start. Circuit breakers provide a manual means of energizing and de-energizing a circuit. In addition, circuit breakers provide automatic overcurrent protection of a circuit. A circuit breaker allows a circuit to be reactivated quickly after a short circuit or overload is cleared. Unlike fuses, which must be replaced when they open, a simple flip of the breaker's operating handle restores the circuit. All circuit breakers perform the following functions: sense when an overcurrent occurs, measures the amount of overcurrent, act by tripping in a timely manner to prevent damage to the circuit breaker and the conductors it protects. In the accompanying illustration, an AC motor is connected through a circuit breaker to a voltage source. When the circuit breaker is closed, a complete path for current exists between the voltage source and the motor, allowing the motor to run. Opening the circuit breaker breaks the path of current flow and the motor stops. The circuit breaker will open automatically during a fault, or can be manually opened. After the fault has been cleared, the breaker can be closed, allowing the motor to operate. Note: Article 240 in the National Electric Code covers overcurrent protection. You are encouraged to become familiar with this information. That concludes Part 1. Let's go into our first knowledge check. Question 1. With an increase in current, heat in a conductor will blank. A. Increase. B. Decrease. C. Stays the same. Question 2. Which of the following is not a cause of overcurrent? Is it A. Ground fault, B. High impedance contact, C. Overload, or D. Short circuit? Question 3. A/N blank is a low resistance path for current created when bare conductors touch. Is it A. High impedance contact, B. Overload, or C. Short circuit? Question 4. A/N blank occurs when too many devices are operated on a single circuit, or when electrical equipment is made to work beyond its rated capabilities. Is it A. High impedance contact, B. Overload, or C. Short circuit? Question 5. Which of the following is a function of a circuit breaker? A. Senses when an overcurrent occurs. B. Measure the overcurrent. C. Act by tripping to prevent damage to itself and associated conductors. Or is it D. All of the above? Now we'll move on to Section 2. This part of Basics of Circuit Breakers covers circuit breaker concepts. Circuit breakers are constructed from the following 5 major components: frame, contacts, arc chute assembly, operating mechanism, and trip unit. The frame provides an insulating housing to mount the circuit breaker components. The construction material is usually a thermoset plastic such as glass polymer. The construction material can be a factor in determining the interruption rating of the circuit breaker. Typical frame ratings include maximum voltage, maximum ampere rating, interrupting rating, and physical size. The current flowing in a circuit controlled by a circuit breaker flows through the circuit breaker's contacts. When a circuit breaker is turned off or is tripped by a fault current, the circuit breaker interrupts the flow of current by separating its contacts. Many circuit breakers use a straight-through contact arrangement, so called because the current flowing in one contact arm continues in a straight line through the other contact arm. As an improvement over the straight-through contact design, Siemens developed the blow-apart contact design now commonly used by circuit breakers with higher interrupting ratings. With this design, the 2 contact arms are positioned parallel to each other as shown in the accompanying illustration. As current flows through the contact arms, magnetic fields are set up around each arm. Because the current flow in one arm is opposite in direction to the current flow in the other arm, the 2 magnetic fields oppose each other. Under normal conditions, the magnetic fields are not strong enough to force the contacts apart. When a fault develops, current increases rapidly, causing the strength of the magnetic field surrounding the contacts to increase as well. The increased strength of the opposing magnetic fields help to open the contacts faster. By reducing the time required to open circuit breaker contacts in the event of a fault condition, the blow-apart contact design exposes the electrical equipment protected by the circuit breaker to less damaging heat. As the contacts open a live circuit, current continues to flow for a short time by jumping the airspace between the contacts in the form of an arc. When the contacts open far enough, the arc is extinguished and the current flow stops. Minimizing the arc is important for two reasons. First, the arc can damage the contacts. In addition, the arc ionizes gases inside the molded case. If the arc isn't extinguished quickly, the pressure from the ionized gases could cause the molded case to rupture. Circuit breakers commonly use an arc chute assembly to quench the arc. This assembly is made up of several U-shaped steel plates that surrounds the contacts. As the arc is developed, it's drawn into the arc chute where it's divided into smaller arcs, which are extinguished faster. A circuit breaker must provide a manual means for energizing and de-energizing the circuit and must be capable of being reset after a fault condition has been cleared. These capabilities are typically provided through use of an operating handle. Molded case circuit breakers are trip-free, meaning that they cannot be prevented from tripping by holding or blocking the operating handle in the on position. There are three positions of the operating handle: on, which is contacts are closed; off, contacts are open; and tripped, mechanism in trip position, contacts open. If a circuit breaker trips, once the fault condition has been corrected, the circuit breaker is reset by moving the handle to the off position and then to the on position. The operating handle is connected to the movable contact arm through an operating mechanism. Siemens multi-case circuit breakers use an over-center toggle mechanism that is a quick make and quick break design. When the operating handle is moved from the off to on position, a spring begins to apply tension to the mechanism. When the handle is directly over the center, the tension in the spring is strong enough to snap the contacts closed. This means that the speed of the contact closing is independent of how fast the handle is operating. The contacts are opened by moving the operating handle from the on to off position. In this process, a spring begins to apply tension to the mechanism. When the handle is directly over the center, the tension in the spring is strong enough to snap the contacts open. As in closing the circuit breaker contacts, contact opening speed is independent of how fast the handle is operated. In addition to providing a means to open and close its contacts manually, a circuit breaker must automatically open its contacts when an overcurrent condition is sensed. The trip unit is the part of the circuit breaker that determines when the contacts will open automatically. In a thermomagnetic circuit breaker, the trip unit includes elements designed to sense the heat resulting from an overload condition and the high current resulting from a short circuit. In addition, some thermomagnetic circuit breakers incorporate a push-to-trip button. The trip unit includes a trip mechanism that is held in place by the tripper bar. As long as the tripper bar holds the trip mechanism, the mechanism remains firmly locked in place. The operating mechanism is held in the on position by the trip mechanism. When a trip is activated, the trip mechanism releases the operating mechanism, which opens the contacts. Some molded case circuit breakers, especially larger breakers, can be manually tripped by pressing the push-to-trip button on the face of the circuit breaker. When the button is pressed, the tripper bar rotates up and to the right. This allows the trip mechanism to unlock, releasing the operating mechanism. The operating mechanism opens the contacts. The push-to-trip button also serves as a safety device by preventing access to the circuit breaker interior in the on position. If an attempt is made to remove the circuit breaker cover while the contacts are in the closed, which is the on position, a spring located under the push button causes the button to lift up and the breaker to trip. Thermomagnetic circuit breakers employ a bimetallic strip to sense overload conditions. When sufficient overcurrent flows through the circuit breaker's current path, heat buildup causes the bimetallic strip to bend. After bending a predetermined distance, the bimetallic strip makes contact with the tripper bar, activating the trip mechanism. A bimetallic strip is made of two dissimilar metals bonded together. The two metals have different thermal expansion characteristics, so the bimetallic strip bends when heated. As current rises, heat also rises. The hotter the bimetallic strip becomes, the more it bends. After the source of heat is removed, as when the circuit breaker contacts open, the bimetallic strip cools and returns to its original condition. This allows a circuit breaker to be manually reset once the overload condition has been corrected. As previously described, current flow through a circuit breaker's blow-apart contacts creates opposing magnetic fields. Under normal operating conditions, these opposing forces are not sufficient to separate the contacts. When a short circuit occurs, however, these opposing forces increase significantly. The current that flows through the contacts also flows through the conductor that passes close to the circuit breaker's trip unit. At fault current levels, the magnetic field surrounding this conductor provides sufficient force to unlatch the trip unit and trip the breaker. The combined actions of magnetic fields forcing contacts apart while simultaneously tripping the circuit breaker result in rapid interruption of the fault current. In addition, because the magnetic forces are proportional to the current, the greater the fault current, the shorter the time it takes to interrupt the current. A thermomagnetic circuit breaker is so called because it has a trip unit that senses heat to detect an overload and senses a magnetic field generated by current to detect a short circuit. As described earlier in the course, this type of circuit breaker trips immediately when a short circuit occurs, but delays an appropriate amount of time before tripping in the event of an overload. As the name indicates, instantaneous magnetic trip-only circuit breakers provide short circuit protection but do not provide overload protection. This type of circuit breaker is typically used in motor control applications where overload protection is provided by an overload relay. For example, in the accompanying illustration, a 3-pole instantaneous magnetic trip-only circuit breaker provides short circuit protection while the overload protection for the motor is provided by an overload relay, which is part of a motor starter. The user cannot change the trip unit on many circuit breakers, but some circuit breakers have an interchangeable trip feature. This feature allows the user to change the continuous current rating of the breaker without replacing the breaker. This is done by replacing the trip unit with one of a different rating. Note: care must be exercised when considering interchangeable trip circuit breakers. A circuit breaker may be listed by UL for a specific interchangeable trip unit only. Circuit breaker frames are usually designed to prevent the installation of an improper trip unit size or type. A molded case switch is a switch that looks like a molded case circuit breaker but does not provide branch circuit protection. Siemens molded case switches have an operating mechanism as similar to that of a thermomagnetic circuit breaker and have a preset instantaneous function factory installed to cause the switch to trip and protect itself at a high fault current. However, these switches provide no thermal overload protection or short circuit protection for a branch circuit. They're primarily used to provide a safe manual means of disconnecting power from a machine or system where overcurrent protection is provided by other components. Many electrical power distribution systems can deliver large short-circuit currents to electrical equipment. This high current can cause extensive damage. Current-limiting circuit breakers protect expensive equipment by significantly reducing the current flowing in the faulted circuit. One way to accomplish current limiting is with an additional set of contacts that feature two movable arms, referred to as a dual pivot contacts, which separate even more quickly than single pivot contacts. The dual pivot contacts are connected in series with single pivot contacts. As with the single pivot design, current flows in opposite directions through the dual pivot contacts arms, creating a magnetic repulsion. As current increases, the magnetic repulsion force increases. In an overload condition where current may only be 1 to 6 times normal current, all contacts remain closed until the breaker trips. When a short circuit occurs, fault current is extremely high and both sets of contact arms open simultaneously, generating high impedance arcs. Because the contact gap of the dual pivot contacts increases more rapidly, the arc impedance also increases more rapidly. Once the arcs are extinguished, the dual pivot contacts close on their own due to spring tension. The single pivot contacts are held open by the breaker mechanism, which tripped during the fault and must be manually reset. The frame on current limiting circuit breakers of this design is extended to allow room for the dual pivot set of contacts. Siemens products include current limiting breakers that can handle fault currents of up to 200,000 amps. Solid-state circuit breakers and thermomagnetic circuit breakers have similar contact mechanisms, but their trip units are different. Like other types of trip units, a solid-state trip unit determines when to trip the circuit breaker. However, a solid-state trip unit allows a circuit breaker to have programmable features and improved accuracy and repeatability. The brain of a solid-state trip unit is a microprocessor. Adjustments on the trip unit set numerical values that the microprocessor uses in performing protective functions. Current sensors connected to the trip unit monitor the load current. The trip unit continuously compares this current to trip unit settings. When current exceeds a preset value for the selected time, the trip unit triggers a magnetic latch. The magnetic latch opens the breaker's contacts, disconnecting the protected circuit from the power source. A circuit breaker's voltage rating is the maximum voltage it can handle. The voltage rating of a circuit breaker can be higher than the circuit voltage but never lower. For example, a 480 volt circuit breaker could be used in a 240 volt circuit, but a 240 volt circuit breaker cannot be used in a 480 volt circuit. The voltage rating is a function of the circuit breaker's ability to suppress the internal arc that occurs when the circuit breaker's contacts open. Some circuit breakers have what is referred to as slash voltage rating, such as 120/240 volts. In such cases, the breaker may be applied in a circuit with a nominal voltage between any conductor and ground does not exceed the lower rating and the nominal voltage between conductors did not exceed the higher rating. A circuit breaker's continuous current rating is the maximum continuous current a circuit breaker is designed to carry without tripping. The continuous current rating is sometimes referred to as the ampere rating because the unit of measures is amperes or amps. The rated current for a circuit breaker is often represented as IN. This should not be confused with the current setting, IR, which applies to those circuit breakers that have a continuous current adjustment. IR is the maximum continuous current that a circuit breaker can carry without tripping for the given continuous current setting. IR may be specified in amps or as a percentage of IN. Conductors are rated for how much current they can carry continuously. This is commonly referred to as a conductor's ampacity. Conductor ampacity is one of the factors that must be considered when selecting and applying a circuit breaker. Siemens circuit breakers are rated using 60 or 75 degrees Celsius conductors. This means that even if a conductor with a higher temperature rating is used, the ampacity of the conductor must be figured on its 60 or 75 degrees Celsius rating. A circuit breaker is also rated according to the maximum level of current it can safely interrupt. This is the interrupting rating, IR, sometimes called the ampere interrupting rating, AIR. Because UL and IEC testing specifications are different, separate UL and IEC interrupting ratings are usually provided. When designing an electrical power distribution system, a main circuit must be selected that can interrupt the largest potential fault current that can occur in the selected application. The interrupting ratings for branch circuit breakers must also be taken into consideration, but these interrupting ratings depend upon whether or not series ratings can be applied. Series connected systems are discussed later in the course. The interrupting ratings for a circuit breaker are typically specified in symmetrical RMS amperes for rated voltages. The term symmetrical indicates that the alternating current value specified is centered around zero and has equal positive and negative half cycles. Siemens circuit breakers have interrupting ratings from 10,000 to 200,000 amps. The circuit breaker frame includes all the various components that make up a circuit breaker except for the trip unit. For any given frame, circuit breakers with a range of current ratings can be manufactured by installing a different trip unit for each rating. The breaker frame size is the highest continuous current rating offered for a breaker with a given frame. Time current curves, similar to the one shown later in the course, are used to show how fast a breaker trips at any magnitude of current. The accompanying illustration shows how to read a time current curve. The horizontal axis shows the multiples of continuous current rating, IN, for the breaker. The vertical axis shows time in seconds. To determine how long a breaker will take to trip at a given multitude of the continuous current rating, find the multiple on the bottom of the graph and draw a vertical line to the point where it intersects the curve. Then draw a horizontal line to the left side of the graph and find the time to trip. For example, in this illustration, a circuit breaker will trip when current remains at 6 times the continuous current rating for 0.6 seconds. Note that the higher the current, the shorter the trip time of the circuit breaker. From the information box in the upper right-hand corner, note that the time current curve shown here defines the operation of a Siemens MG frame circuit breaker. For this example, operation with an 800 amp trip unit is shown, but depending upon the specific breaker chosen, the circuit breaker may be purchased with a 600, 700, or 800 amp continuous current rating. The top part of the time current curve shows the continuous current performance of the circuit breaker. The black line shows the nominal performance of the circuit breaker, and the gray band represents possible variation from this nominal performance that can occur even under specified conditions. Using the example of the MG breaker with an 800 amp continuous current rating, IN, note that the circuit breaker can be operated at 800 amps, 1.0 times IN, indefinitely without tripping. However, the top of the trip curve shows that an overload trip will occur in 10,000 seconds at 1,000 amps, 1.25 times IN. Additionally, the gray area on either side of the trip curve shows the range of possible variation from this response. Keep in mind that the trip curve was developed based upon predefined specifications, such as operation at 40 degrees Celsius ambient temperature. Variations in actual operating conditions will result in variations in circuit breaker performance. The middle and bottom parts of this time current curve show the instantaneous trip performance of the circuit breaker. Note that the maximum clearing time, which is the time it takes for the breaker to completely open, decreases as current increases. This is because of the high-speed contact designs which utilize the magnetic field built up around the contacts. As current increases, the magnetic field strength increases, which speeds the opening of the contacts. This circuit breaker has an adjustable instantaneous trip point from 3250 to 6500 amps, which is approximately 4 to 8 times the 800 amp continuous current unit rating. This adjustment affects the middle portion of the trip curve, but not the top or bottom parts of the curve. The breaker shown in this example has a thermomagnetic trip unit. Circuit breakers with solid-state trip units typically have additional adjustments. Selective coordination is the application of circuit protected devices in series such that, when a fault occurs, only the device nearest the fault opens. The rest of the devices remain closed, leaving other circuits unaffected. In this example shown here, a short circuit has occurred and the circuit fed by branch circuit breaker C. Power is interrupted to equipment supplied by circuit breaker C only. All other circuits remain unaffected. Time current curves are essential for coordinating circuit breakers. For example, in the accompanying illustration, the trip curves of main breaker A, feeder breaker B, and branch breaker C are placed on the same graph and there is no overlapping, indicating that the breakers are coordinated. These circuit breakers have been coordinated so that, for any given fault value, the tripping time of each breaker is greater than tripping time for the next downstream breaker. In this example, circuit breaker C is set to trip if a 400 amp fault current remains for 0.04 seconds. Circuit breaker B will trip if the fault remains for 0.15 seconds, and circuit breaker A will trip if the fault remains for 0.8 seconds. If a 400 amp fault occurs downstream from circuit breaker C, it will trip and clear the fault, and circuit breakers A and B will not trip. NEC Article 110.9 requires circuit protection equipment to have an interrupting rating sufficient for the available current. There are 2 ways to achieve this requirement: the full rating method and the series rating method. The full rating method requires all circuit protection devices to have an interrupting rating equal to or greater than the available fault current. This means that in the case of a building with 65 amps of fault current available at the service entrance, every circuit breaker must have an interrupting rating of at least 65,000 amps. The second method is to select circuit breakers with a series combination rating equal to or greater than the available fault current at the service entrance. The series rated concept requires the main breaker to have an interrupting rating equal to or greater than the available fault current of the system, but subsequent downstream breakers connected in series can be rated at lower values. For example, a building with 65,000 amps of available fault current might only need the breaker at the service entrance to have an interrupting rating of 65,000 amps. Additional downstream breakers can be rated at lower values. The series combination must be tested and listed by UL. That completes Section 2. On to the next knowledge check. Question 1. Blank circuit breakers trip when a short circuit occurs, but do not provide overload protection. Is it A, thermomagnetic, B, instantaneous magnet trip only, C, solid state? Question 2. The maximum continuous current a circuit breaker can carry without tripping is its continuous current rating, which is often called its blank rating. Is it A, ampere, B, ampacity, C, voltage, or D, interrupting? Question 3. The top part of a circuit breaker's time current curve shows the blank performance of the circuit breaker. Is it A, instantaneous trip, B, continuous current, or C, short circuit? Question 4. The middle and bottom part of a circuit breaker's time current curve shows the blank performance of the circuit breaker. Is it A, overload protection, B, instantaneous trip, or C, continuous current? Question 5. The blank rating method requires all circuit breakers to have interrupting ratings equal to the available fault current. Is it A, full, B, selective coordination, or C, series? Section 3 of this course covers various Siemens molded case circuit breakers. Siemens offers a broad selection of circuit breakers. The remainder of this course provides a brief overview of Siemens circuit breakers in the following categories: residential circuit breakers, panel board circuit breakers, general purpose thermomagnetic circuit breakers, solid state trip unit circuit breakers, VL and WL circuit breakers. Because this course is intended to provide only an overview of Siemens circuit breakers, some Siemens circuit breaker types are not included. However, understanding the types of circuit breakers summarized in this course will provide you with a good foundation for further study. Siemens offers a wide selection of load centers and enclosures equipped with a main circuit breaker. Additionally, Siemens PL load centers are convertible from main breaker load centers to main lug load centers and vice versa. The main breakers or main breaker kits for PL load centers have continuous current ratings from 100 to 225 amps. The interrupting rating for these main breakers is 22 kA. Single-phase factory installed 22 kA interrupting rating main circuit breakers offer a 2210 kA series combination interrupting rating when used with 10 kA type QP, QT, QPF, QE, QN, and QAF branch breakers. In addition, the thermomagnetic circuit breakers, intended for use as main or branch circuit breakers in residential applications, Siemens offers branch circuit breakers with arc fault circuit interruption, ground fault circuit interruption, or point of entry surge protection. Circuit breakers are also available for a number of special applications. All Siemens residential circuit breakers provide overload and short circuit protection. Because of the variety of circuit breakers offered, this course describes only representative examples. Residential circuit breakers are typically 1-pole, 2-pole, or 4-pole breakers with current ratings of 225 amps or less and voltage ratings of 120 volt, 12240 volt, or 240 volt. Because residential circuit breakers are also used in commercial applications, and many commercial applications require 3-pole breakers, some 3-pole breakers are also included in this category. Residential circuit breakers are normally plug-in types that mount in load centers or other enclosures. Because Siemens offers a complete selection of load centers and other enclosures, and application requirements for circuit breakers vary, multiple branch circuit breaker types are also needed. However, type QP and QT circuit breakers discussed in this course provide a representative sampling. Type QP circuit breakers are available as 1-pole, 2-pole, or 3-pole breakers. 2-pole and 3-pole varieties have a common trip unit so that all breaker poles are tripped at the same time. Single-pole QP breakers are rated for 120 volt and have continuous current ratings from 10 to 70 amps. 2-pole QP breakers are available with a 122/40 volt rating or a 240 volt rating. 2-pole 122/40 VAC QP breakers have continuous current ratings from 10 to 125 amps, and 2-pole 240 volt QP breakers have continuous current ratings from 15 to 100 amps. 3-pole QP breakers are rated for 240 volt and have continuous current ratings from 10 to 100 amps. All type QP circuit breakers have 10 kA interrupting rating. However, Siemens also offers type QPH circuit breakers with a 22 kA interrupting rating and type HQP circuit breakers with a 65 kA interrupting rating. Some Siemens load centers are designed to accept QT duplex, QT triplex, and QT quadplex plug-in breakers. These breakers are space-saving breakers that are half the width per pole of type QP circuit breakers. This reduced width allows more circuits to be serviced from a load center, provided that the main circuit breaker has sufficient capacity. Another important use for QT breakers in this case where additional circuits are being added to an existing load center, but the number of spaces available in the load center is limited. Type QT duplex circuit breakers combine two independent half-inch width breaker poles in one common unit. This unit plugs into one load center stab and requires one panel space. Type QT circuit breakers are also available in triplex and quadplex configurations. QT triplex incorporates a 2-pole circuit breaker for 122/40 volt circuits and two independent 1-pole circuit breakers for 120 volt circuits. QT quadplex incorporates two common trip 2-pole circuit breakers for 122/40 volt circuits. Each QT quadplex or QT triplex circuit breaker requires two panel spaces. A ground fault occurs when a current carrying conductor comes in contact with ground. A ground fault circuit interrupter, a GFCI, compares current on the hot wire with current returning on the neutral wire. Under normal circumstances, these currents are equal. Siemens type QPF and QPHF GFCI circuit breakers provide personal protection by de-energizing a circuit when a ground fault current of 6 milliamps or more is sensed. Siemens also offers type QE and QEH circuit breakers which provide protection of equipment from damaging line-to-ground faults by de-energizing a circuit when a ground fault current of 30 milliamps or more is sensed. Arc fault circuit interrupter, AFCI, circuit breakers, such as Siemens type QAF and QAFH breakers, help mitigate the risk of a fire being started from an unintended arc by de-energizing a circuit when an arc fault is detected. An arc fault occurs when a current-carrying conductor arcs to ground, to another conductor, or to another point on the same conductor. Damaged insulation can lead to an arc fault, which may not generate enough fault current to trip a standard circuit breaker. An AFCI circuit breaker, in addition to providing overcurrent protection, is intended to provide protection from the effects of arc faults by recognizing the characteristics unique to arcing and de-energizing the circuit when an arc fault is detected. There are two categories of AFCI circuit breakers on the market: the branch feeder AFCI circuit breakers and the combination AFCI, the CAFCI circuit breakers. The first AFCI circuit breakers developed were branch feeder AFCI circuit breakers that, in addition to providing overcurrent protection, are intended to protect branch and feeder wiring from the damaging effect of line-to-ground arcs and high-energy parallel arcs. High-energy parallel arcs are line-to-neutral arcs greater than or equal to 75 amps. More recently, combination arc fault circuit breakers have been developed. The CAFCI circuit breakers, in addition to providing overcurrent protection, are intended to protect downstream wiring from three categories of arc faults: line-to-ground, high-energy parallel, and series arcs greater than or equal to 5 amps. Series arcs are arcs on a single conductor. Requirements for arc fault circuit interrupter protection are covered in NEC Article 210.12. Over the years, the wording of this article has evolved. Refer to the appropriate version of the code for your location to determine requirements for AFCIs and CAFCIs. Siemens type QAF AFCI circuit breakers have a 10 kA interrupting rating, and type QAFH AFCI circuit breakers have a 22 kA interrupting rating. Both breakers are available in single pole and two pole versions. Siemens offers a variety of devices intended to minimize damage from electrical surges. One of these devices, the Siemens Circuit Breaker and SPD surge protection device, incorporates two independent single pole 15 or 20 amp circuit breakers and provides surge protection for all branch circuits. The majority of Siemens thermomagnetic circuit breakers intended for commercial and industrial applications are classified in the SpeedFacts catalog as general purpose breakers. Some of these breakers are used in panel boards. However, Siemens Type BL, BLH, HBL, BQD, and BQD6 circuit breakers are intended exclusively for panel board use. These are thermomagnetic circuit breakers with features similar to those of the residential circuit breakers discussed previously. Whereas many of the residential breakers plug into their enclosures, the panel board breakers listed in this section bolt onto the panel board's power bus. Type BL, BLH, and HBL circuit breakers are available in single pole, two pole, or three pole versions. Also included in this category are circuit breakers that incorporate the following capabilities: ground fault circuit interruption. Those are types BLF and BLHF. Ground fault equipment protection. Those are the BLE and the BLEHs. Arc fault circuit interruption. Types BAF and BAFH, or switching neutrals. That's type BG. Additionally, versions of the BL breaker are available which can accommodate the high inrush current associated with high intensity discharge, HID, or the tungsten lighting and a molded case switch for use where overcurrent protection is provided separately. Type BQD and BQD6 circuit breakers are 100 amp frame breakers available in single pole, two pole, and three pole versions. BQD6 breakers are CSA certified. For the purpose of this course, Siemens thermomagnetic circuit breakers type BQ, CQD, NGG-NGB, EG-EB, ED, FD, JD, LD, LMD, MD, ND, PD, RD, and variants of these types are classified as general purpose circuit breakers. As such, they are used in commercial and industrial applications in a variety of enclosure types. Type BQ, BQH, and HBQ plug-in circuit breakers are available with 1, 2, or 3 poles. These circuit breakers are supplied with load-side lugs, but may be ordered with line-side lugs. Additional versions are available for DIN rail mounting. Type CQD circuit breakers are 100 amp frame breakers similar to BQD circuit breakers, but equipped for DIN rail mounting. Type CQD6 breakers are CSA certified rather than UL listed. Type NGG and NGB circuit breakers are 125 amp frame breakers that are smaller in size than comparable type ED breakers. NGG breakers come equipped for DIN rail mounting, but alternative mounting hardware is also available. NGB circuit breakers are intended for use as main circuit breakers in Siemens P1 and P2 panel boards and as a branch circuit breaker in Siemens P1, P2, P3, P4, and P5 panel boards. They are also used in the distribution section of Siemens switchboards. Interrupting ratings for NGG and NGB circuit breakers depend upon the applied voltage, but most notably, these breakers have a 65 kA interrupting rating at 240 volts. Additionally, although NGB breakers carry a 25 kA interrupting rating at 480/277 volts, they're applied in Siemens panel boards and switchboards at 22 kA rated for single pole and 18 kA rated for 2 and 3 poles. Type EG and EB circuit breakers are also 125 amp frame breakers that are smaller in size than comparable type ED circuit breakers. These breakers carry an N or H prefix dependent upon their interrupting rating. N is normal, H is high. EG circuit breakers can be mounted on a DIN rail with an adapter base or held in place by mounting screws. EB circuit breakers are intended for use as branch circuit breaker in Siemens P3, P4, and P5 panel boards, and the distribution section of Siemens switchboards. The EG family also includes type HEM motor circuit protectors and type HES molded case switches. HEM motor circuit protectors have continuous current ratings from 3 to 100 amps. HES molded case switches are available in 3-pole or 4-pole versions with continuous current ratings of 100 or 125 amps for 3-pole switches and 125 amps for the 4-pole switches. Type ED, FD, JD, LD, LMD, MD, ND, PD, and RD thermomagnetic circuit breakers provide a range of frame sizes from 125 amp frame ED circuit breakers to 2000 amp frame RD circuit breakers. For simplicity, the accompanying graphic shows only the smallest and largest frame sizes. Each of these types has variations that are indicated by an H or HH prefix to indicate a high interrupting rating or a C prefix to indicate a fuseless current limiting circuit breaker. These designations also coincide with label colors. Standard circuit breakers have a blue label, breakers with H and HH prefixes have a black label, and breakers with a C prefix have a red label. FD, JD, LD, LMD, MD, ND, PD, and RD circuit breakers, including breakers with H or HH prefixes, are designated as a complete breaker unassembled with lugs, indicating that they include a frame, interchangeable trip unit, and line side and load side lugs in separate packages. For applications requiring non-standard lugs, separate lugs must be ordered. Where the type designation includes an X or has a C prefix, the breakers are designated as a complete breaker assembled without lugs, indicating that the breaker has been assembled with a non-interchangeable trip unit and lugs must be ordered separately. All circuit breakers with the X designation, such as JXD2 and JXD6 breakers, are UL listed for reverse feed applications. This means that power can be applied to the load side of the circuit breaker. Selected circuit breakers are available as an instantaneous magnetic trip circuit breaker for use in motor circuits where motor overload protection is provided separately. Additionally, a few types are available as a molded case switch. Type SJD, SLD, SMD, SND, and SPD circuit breakers are similar to type JD, LD, MD, ND, and PD circuit breakers, but are equipped with a solid-state trip unit. Solid-state trip units make it possible to precisely match overcurrent protection to application requirements. Siemens solid-state trip unit circuit breakers incorporate true root mean square (RMS) sensing to accurately sense the effective value of the circuit current. True RMS sensing is accomplished by taking multiple instantaneous samples of the actual current wave shape for a more accurate picture of its true heating value. In addition to the standard circuit breaker types SJD6, SLD6, SMD6, SND6, and SPD6, which carry a blue label, this family includes high interrupting rating types SHJD6, SHLD6, SHMD6, and SHPD6, which have a black label, and current limiting types SCJD6, SCLD6, SCM6, and SCND6, which have a red label. SMD6-H, SHMD6, SCMD6/H, SND6/H, SHND6, and SCND6/H 100% rated breakers are also available. One of the key features of the solid-state trip unit circuit breakers is the ability to make selective adjustments to the circuit breaker's time current curve. The time current curve shown here is for a circuit breaker in the SJD6-SPD6 family. Solid-state trip units can have adjustments for long time pickup, long time delay, short time pickup, short delay, instantaneous pickup, ground fault pickup, and ground fault delay. The adjustments available depend upon the specific model. The type of trip unit included in an SJD6, SLD6, SMD6, SND6, or SPD6 circuit breaker determines the specific time current curve adjustments available. Breakers in this family may be ordered with any of 4 trip unit types. Refer to the speed facts for a listing of the adjustments available with each trip unit type. Circuit breakers typically have optional accessories for mounting, connecting, and securing the circuit breaker and remotely indicating the circuit breaker's contact status. A few examples of circuit breaker accessories are described in this course, but others are commonly available. Because circuit breakers are often located far from operating equipment, it's sometimes necessary to trip a breaker remotely so that equipment can be stopped rapidly. For this reason, a circuit breaker shunt trip device is sometimes wired to a push button located on or near an operator panel. The shunt trip device consists of a coil in series with a limit switch. When the circuit breaker main contacts are closed, the limit switch is closed. Pressing a customer-supplied push button energizes the shunt trip coil, which causes the breaker's mechanical latch to disengage the trip mechanism and open the circuit breaker's contacts. When the circuit breaker's contacts open, the limit switch also opens, removing power from the shunt trip coil. As with any trip, the breaker must reset manually. The undervoltage trip device is designed to automatically trip the circuit breaker when the supply voltage drops to a low value, 35 to 70% of nominal line voltage. The device also prevents the circuit breaker from being reset until the supply voltage returns to at least 85% of its normal level. Common voltages for shunt trip and undervoltage trip coils are 24 VDC, 48 VDC, 125 VDC, 120 VAC, 240 VAC, and 480 VAC. An auxiliary switch is an accessory that can be wired to a circuit that indicates the position of the circuit breaker's main contacts. For example, in the circuit shown on the left in the accompanying illustration, contact A is closed and the indicator light is on when the circuit breaker is on. At the same time, contact B is open. If the circuit breaker is tripped or turned off, the states of the auxiliary switch contacts change and the light goes out. The bell alarm switch differs from the auxiliary switch in that it only functions when the circuit breaker trips. Opening and closing the circuit breaker by means of the operating handle does not affect the position of the bell alarm switch contacts. In the circuit shown on the right in the accompanying illustration, the A contact closes and the B contact opens when the circuit breaker trips. An audible alarm or indicator light can be used to indicate the circuit breaker has tripped. Time for another knowledge check. Question 1. Which of these Siemens residential circuit breakers requires only one load center space? Is it A, circuit breaker and SPD, B, QT duplex, C, QT triplex, or D, QT quadplex? Question 2. Which of these Siemens circuit breaker types is not a 125 amp frame breaker? Is it A, NGG, B, NGB, C, ED, or D, CQD? Question 3. Which of these Siemens circuit breaker types has the largest frame size? Is it A, BQ, B, HHED6, C, RD6, or D, SJD6? Question 4. Which of these Siemens circuit breaker types has a solid-state trip unit? Is it A, JD6-A, SJD6, HJD6-A, or CJD6? Question 5. Which of these circuit breaker accessories allows a user to remotely trip a circuit breaker? Is it A, shunt trip, B, undervoltage trip, C, auxiliary switch, or D, bell alarm switch? Okay, last section. This part of the basics of circuit breakers covers Siemens VL molded case circuit breakers and Siemens WL insulated case and low voltage power circuit breakers. Siemens VL family of circuit breakers incorporates a compact modular design that allows these breakers to be configured to match a wide range of applications. Additionally, VL circuit breakers have been engineered to meet global requirements and carry the markings shown in the accompanying graphic. The VL family includes frame sizes from 150 to 1600 amps. The following 3 interrupting rating classes are available for each circuit breaker frame: N for normal, H for high, or L for very high. One of the many aspects of the VL circuit breaker family is the flexibility of each VL circuit breaker frame to accommodate any of the following 3 available trip units: Model 525 thermomagnetic trip unit, Model 555 electronic trip unit, Model 586 electronic trip unit with LCD. The VL family also includes multi-case switches, motor circuit protectors, and other complete breakers with non-interchangeable trip units. Internal accessories for VL breakers are field installable and are conveniently located in pockets behind the front accessory cover. To simplify the selection of accessories, just 2 groups of internal accessories cover the entire VL family. Additional external accessories are also available to accommodate a wide variety of application requirements for connecting, mounting, and operating VL circuit breakers. Communications modules are available for connecting to Modbus or Profibus DP systems. The accompanying illustration identifies the array of trip units, options, and accessories for use with VL circuit breakers. VL circuit breakers are available with multiple frame sizes, from DG 150 amp frame size to PD 1600 amp frame size. Each frame size is available in 3 interrupting rating classes designated by a preceding N, H, or L. 3 trip unit models, 525, 555, and 586, are available for each VL circuit breaker type. Model 525 thermomagnetic trip units are available with multiple continuous current ratings. For example, MG frame circuit breakers can be equipped with a 600 amp, 700 amp, or 800 amp model 525 trip unit. The time current curve shown here is for an 800 amp model 525 trip unit. Note that while the continuous current rating is set by the selection of the trip unit, the instantaneous pickup setting is adjustable. Model 555 electronic trip units allow the user to adjust a circuit breaker's time current curve to provide optimal protection and avoid nuisance tripping. Model 555 trip units are available with multiple maximum continuous current ratings. For example, MG frame circuit breakers can be equipped with a 600 or 800 amp model 555 trip unit. Which protective functions are provided by a Model 555 trip unit depends on the trip unit version. Model 555 trip units may be ordered with LI, LSI, LIG, or LSIG functions. The letter designations used to identify these functions are based on recognized international standards and can be described as follows. L equals long-term pickup and delay, which equals overload protection. S equals short time pickup and delay, which equals short circuit protection, or short time delayed. I equals instantaneous, which equals short circuit protection, no delay. And G equals ground fault pickup and delay, which equals ground fault protection. The characteristics of a time current curve for a VL circuit breaker with a Model 555 trip unit depends on the specific trip unit selected and whether the I2T, I2T function is turned on. The time current curve shown here identifies important time current characteristics for an 800 amp Model 555 trip unit with LSI protection and I2T turned on. The Model 555 trip unit permits communication with the Modbus RTU or Profibus DP communication module. Model 586 electronic trip units with LCD also allow the user to adjust the circuit breaker's time current curve to provide optimal protection and avoid nuisance tripping. The liquid crystal display, LCD, provides a user-friendly menu-driven method for setting protection parameters and continuously shows the current for each phase. Model 586 trip units are available with multiple maximum continuous current ratings. For example, MG frame circuit breakers can be equipped with a 600 or 800 amp Model 586 trip unit. Model 586 trip units are equipped with LSI, LSIG, or LSI plus G-alarm only protective functions. The characteristics of a time current curve for a VL circuit breaker with Model 586 trip unit depend on the specific trip unit selected and whether the I2T function is turned on. The time current curve shown in the accompanying graphic identifies important time current characteristics for an 800 amp Model 586 trip unit with LSI protection and I2T turned on. The Model 586 trip unit permits communication with the Modbus RTU or Profibus DP communications module. Siemens WL family of circuit breakers has been designed to address the increasingly demanding requirements of today's electrical power distribution systems and incorporates the following characteristics: high reliability, compact size, ease of use, modularity of design, flexibility of system communications, safety-oriented features. The circuit breakers discussed thus far in this course are molded case circuit breakers that conform to the UL 489 specification. This specification also covers a category of molded case circuit breaker commonly referred to as an insulated case circuit breaker, an ICCB. ICCBs are generally used in switchboards and may be fixed mounted or drawer-out mounted. Another category of low voltage circuit breakers is the LV power circuit breaker. LV power circuit breakers are generally drawer-out mounted and may be used in switchboards or switchgear. LV power circuit breakers intended for the U.S. market conform to American National Standards Institute, the ANSI, standards C37.13, C37.16, C37.17, and C37.50, and National Electrical Manufacturers Association NEMA standard SG3. The corresponding UL specification for LV power circuit breakers is UL 1066. Siemens' WL family of circuit breakers includes both ICCBs that conform to the UL 49 specification and LV power circuit breakers that conform to the UL 1066 and corresponding ANSI and NEMA specifications. WL UL 489 circuit breakers have a rated maximum operating voltage of 600 volts and are available in 3 frame sizes with frame ratings from 800 to 5000 amps. All 3 frame sizes have fixed mounted and draw-out mounted versions. WL UL 1066 circuit breakers are generally used in low voltage switchgear as draw-out mounted breakers, have a rated maximum operating voltage of 635 volts, and are available in 2 frame sizes with frame ratings from 800 to 5000 amps. One important low voltage power circuit breaker rating is its short time withstand current rating. This rating indicates the level of current that a breaker can handle without damage for a designated short time. This rating is important because an LV power circuit breaker is often required to delay tripping for a short time when a fault current is sensed so that a downstream breaker closer to the fault has time to trip, thereby avoiding a larger system outage. WL circuit breakers have a flexible modular design that includes common plug-in accessories, field upgradable trip units, and field changeable contacts and arc chutes. This design minimizes inventory, allows for last-minute changes, and is cost-effective to support. WL circuit breakers can be fused or unfused and delivered with any of these operating mechanisms. Manual operating mechanism with mechanical closing, which is standard. Manual operating mechanism with mechanical and electrically interlock closing. Motorized operating mechanism with mechanical and electrically interlock closing. WL circuit breakers have a number of standard and optional features that enhance the safety and usability of the breaker, reduce errors, and minimize training time. The accompanying graphic shows some of the features that can be seen from the front. 3 electronic trip units are available for use with WL circuit breakers. The protective functions, display types, and communication options available for these trip units are shown in the accompanying diagram. A few of the additional capabilities include dual parameter sets, dynamic arc flash sentry, and extended instantaneous protection. Dual parameter sets is a feature of ETU 776 trip units that simplifies adapting the system to rapid changes, such as when power is switched between utility power and a generator. Switching between parameter sets can be done quickly and, if desired, remotely. Dynamic Arc Flash Sentry employs the unique dual protection settings of ETU 776 trip units coupled with the ability to toggle to a lower arc flash parameter set. A normal parameter set can be optimized for selective trip coordination with the alternate parameter set optimized for lower arc flash energy levels initiated when a personnel approach the arc flash protection boundary. Extended instantaneous protection, available with all 3 trip units, is designed to provide any WL low voltage power circuit breaker with the capability to be applied at the short time withstand rating of the breaker with no instantaneous override. This feature gives downstream breakers the maximum possible time to clear a fault and reduces the likelihood of a system-wide outage. That concludes section 4. Let's do a final knowledge check and then we'll head right into the final exam. Question 1. Siemens VL circuit breakers are available with continuous current ratings up to, is it A, 800 amp, B, 1200 amp, C, 1600 amp, or D, 2000 amp? Question 2. Which of these VL circuit breaker trip units is a thermal magnet trip unit? Is it A, model 525, B, model 555, C, model 586, or D, none of the above? Question 3. Siemens WL circuit breaker family includes insulated case circuit breakers that conform to the UL blank specification and low voltage power circuit breakers that conform to the UL blank specification. Is it A, 489, 1066, B, 1950, 1977, C, 218, 231, or is it D, none of the above? Question 4. Siemens WL circuit breakers are available in fixed mounted and draw-out mounted versions. Is that A, true, or B, false? Question 5. Siemens WL circuit breakers are available with continuous current ratings up to blank. Is it A, 2000 amp, B, 3000 amp, C, 4000 amp, or D, 5000 amp? Let's begin our final exam. Question 1. With an increase in current, temperature will blank. Is it A, decrease, B, increase, C, stay the same, or D, fluctuate? Question 2. The amount of current a conductor can carry continuously is known as its, is it A, ampacity, B, instantaneous current rating, C, peak current rating, or D, AWG? Question 3. A blank circuit breaker contact design uses magnetic fields developed around the contacts to help force them apart during an overcurrent condition. Is it A, straight through, B, single pivot, C, dual pivot, or D, blow apart? Question 4. Siemens multi-case circuit breakers use A/N blank toggle mechanism that is a quick make and quick break design. Is it A, over center, B, center off, C, normally closed, or D, normally open? Question 5. The blank is the part of a circuit breaker that determines when the breaker will trip. Is it A, arc chute assembly, B, trip unit, C, frame, or D, operating mechanism? Question 6. A/N blank provides both overload and short circuit protection. Is it A, instantaneous magnet trip only circuit breaker, B, multi-case switch, C, thermal magnetic circuit breaker, or is it D, overload relay? Question 7. A circuit breaker, blank, includes all the various components that make up a circuit breaker except a trip unit. Is it A, internal accessory, B, external accessory, C, instantaneous trip, or is it D, frame? Question 8. The uppermost portion of a circuit breaker time current curve shows the blank performance of the circuit breaker. Is it A, instantaneous trip, B, short circuit, C, continuous current, or D, current limiting? Question 9. Which of these Siemens circuit breakers has the same 1-inch width as a Siemens QP circuit breaker? Is it A, QT duplex, B, QT triplex, C, QT quadplex, or D, all of the above? Question 10. The application of circuit protective devices in series such that, when a fault occurs, only the device nearest the fault will open is known as, is it A, selective coordination, B, the series rating method, C, the full rating method, or D, current limiting? Question 11. What type of arc fault will trip a Siemens combination AFCI circuit breaker? Is it A, line to ground, B, high energy parallel, C, series arcs greater than or equal to 5 amps, or D, all of the above? Question 12. Which of these Siemens circuit breakers incorporates two independent, single pole, 15 amp or 20 amp circuit breakers and provides surge protection for all branch circuits? Is it A, circuit breaker and SPD, B, QT duplex, C, QAF AFCI circuit breaker, or D, QE GFCI circuit breaker? Question 13. Which of these Siemens circuit breaker types has the largest frame size? Is it A, BQ, B, HHED6, C, RD6, or D, SJD6? Question 14. Which of these Siemens circuit breaker types has a solid-state trip unit? Is it A, JD6-A, B, SJD6, C, HJD6-A, or D, CJD6? Question 15. Which of these circuit breaker accessories allows a user to remotely trip a circuit breaker? Is it A, shunt trip, B, undervoltage trip, C, auxiliary switch, or D, bell alarm switch? Question 16. Which of the following letter designations is used to indicate that a trip unit provides overload protection? Is it A, L, B, S, C, I, or D, G? Question 17. Which of the following Siemens VL circuit breaker trip unit models is an electronic trip unit with an LCD? Is it A, model 515, B, model 525, C, model 555, or D, model 586? Question 18. Siemens VL circuit breakers are available with continuous current ratings up to, is it A, 800 amp, B, 1200 amp, C, 1600 amp, or D, 2000 amp? Question 19. Siemens WL circuit breakers are available with continuous current ratings up to blank. Is it A, 2000 amps, B, 3000 amps, C, 4000 amps, or D, 5000 amps? Question 20. Siemens WL circuit breaker family includes insulated case circuit breakers that conform to UL blank specification and LV power circuit breakers that conform to UL blank specification. Is it A, 489 1066, B, 1950 1977, C, 218 231, or D, none of the above? Well, that concludes the Siemens Quick Step Basics of Circuit Breakers. Thanks again for your time and attention.